In this video, we'll see how we can use a service called an API to acquire data for our data science workflows. We've already established that you can't always rely on tidy tabular data to just come along and land on your desk. Sometimes you're going to have to go out there and gather it for yourself. We've already seen how to scrape information directly from the HTML source of a web page, but surely there has to be an easier way for us to get this information. And thankfully, in lots of cases, there often is. In this video, we'll cover the basics of obtaining data via an application programming interface. This material draws together the Introduction to APIs book written for Zapier by Brian Cooksey, and the DIY web data section of the Stat 545 course at the University of British Columbia, which was developed by Jenny Bryan, who we've mentioned many times already. So, why exactly do you need to know about APIs as a data scientist? Well, as a data scientist, you'll often need to access data that's stored on a remote server or in cloud based services. APIs provide a convenient way for data scientists to retrieve this data programmatically without having to manually download datasets or process them locally on their own computer. When it comes down to it, an API, or application programming interface, is just a set of rules that allows different software applications to communicate with each other. Using an API over sending CSV files or other data files directly has multiple benefits, but the main ones are automation and standardization of the data sharing process. In terms of automation, it's much faster for a machine to process a data request than it is for a human to do so. Having a machine handling these data requests also scales much better as the number of requests grows or the complexity of those requests also grows. Additionally, there's going to be a lower risk of introducing human error during this process. For example, a human might accidentally share the wrong data, and that can have some really serious legal repercussions. There are also benefits in terms of standardization of the data acquisition process. If you've got a machine handling this process, that means that you're going to have to come up with a standardized format for these requests to be placed and a standardized format for the associated responses. This allows us to include the data sharing and retrieval process as a part of our reproducible and programmatic workflow. Okay then, so if APIs are so great, what exactly are they? Well, in human-to-human communication, the set of rules governing acceptable behavior is known as etiquette. Depending on where or when you happen to be alive, social etiquette can be really rather strict, but the rules for computer-to-computer communication take this to a whole new level, because with machines, there can be no room left for any sort of interpretation. The set of rules governing interactions between computers or different programs on the same computer is known as a protocol. An API provides a standard protocol for different programs to interact with each other. This makes life easier for developers because it allows them to build complex systems by leveraging the functionality of existing services and platforms. The benefits of working in a standardized and modular way apply equally well to sharing data as they do to writing code or organizing files. So, in any communication, there are two sides, and when machines communicate, these are known as the server and as the client. Servers can be quite intimidating to people because, unlike your laptop or mobile phone, they don't have their own input and output devices. They've got no keyboard, no monitor, or no mouse. Despite this, though, servers are just like regular computers that are designed to store and run programs. They just might be slightly better at it than your laptop or your phone are. The reason that servers don't have their own input or output devices is because they're intended to be used remotely via another computer. There's no need for a screen or a mouse if the user is miles away. So really, there's nothing scary going on here and nothing to be afraid of. On the flip side, people often find clients much less intimidating because these are simply any other computer or application that might want to contact the server. Okay, so then this leads us one step further down the rabbit hole. An API is a protocol that defines how applications communicate with each other. But how exactly does this communication even happen? HTTP, or Hypertext Transfer Protocol, is the dominant mode of communication on the World Wide Web. You can see the secure version of HTTP, HTTPS, at the start of most web addresses at the top of your browser. So, for example, at the start of the Imperial website. HTTP is the foundation of data communication on the web, and it's used to transfer files like text, images, or videos between web servers and web clients. To understand HTTP communications, I find it quite helpful to imagine the client and the server as being a customer and a waiter at a restaurant. The client makes some request to the server, which then tries to comply before giving a response back to the client. The server might respond to confirm that the request was completed successfully, or alternatively, the server might respond with an error message, which is a hopefully informative summary of why the request couldn't be completed. This type of request response model is the basis for HTTP, the same communication model that's used by APIs. So let's look in a little bit more detail now at the structure of a HTTP request. A request has four main parts. The first is a URL, or Uniform Resource Locator. This is a unique identifier for a thing on the internet. Colloquially, it's known as a web address, and a URL can point towards any sort of object. It might be a web page, but it can also point to a file, like an image or document, or else to an application or some other form of software. In the case of getting data, the URL will be used for database access. The method within a HTTP request tells the server the type of action that the client has requested, and we'll see some example methods coming up shortly. The request headers then contain meta information about the request. So, for example, this might be the type of device that the request was made from, and this is important for web pages so that you get the correct mobile or desktop version, for example. Finally, the body of the request contains any data that the client wants to send to the server. So this might be the data that you want to store in a remote backup, for example. The action that a client wants to take is indicated by a set of well-defined methods, or HTTP verbs. The most common of these verbs are get, post, put, patch, and delete. The get verb is used to retrieve a resource from the server, such as a web page or an image. The post verb is used to send data to the server, such as when submitting a form or uploading a file. The put verb is used to replace a resource on the server with a new one, while the patch verb is used to update a resource on the server without replacing it entirely. Finally, the delete verb is used to delete a resource from the server altogether. In addition to this set of common HTTP verbs, there are also several less frequently used ones. These are used for specialized purposes like requesting only the headers of a resource or testing the connectivity between the client and the server. In terms of data acquisition, we're really going to be focusing on GET requests here, but the others will be useful if further down the line you want to set up your own API and share data with others, in which case you're going to have to manage the data that is stored. So let's look at the response now. When the server receives a request, it'll attempt to fulfill it and then send some sort of response back to the client. A response has a similar structure to the request, apart from a few key differences. So there's no URL in a response and there's no method. But what we do have that we don't have in a request is a status code. And this is a 3-digit number where each number has a specific meaning. Some common error codes that you might have already come across are the 404 code in particular for a page not found, and all 400s status codes indicate errors. But you might also have seen a 503 indicating that a page was down, or what you probably haven't seen is a 200 code, because that indicates that the page has been loaded successfully. When we're retrieving data, we're really hoping for this 200 code. That means our data request has been successful, and the API has given us back some data in either JSON or XML format, typically. Now that we know how applications communicate, you might ask how we control who has access to the API and what types of requests they can make. This can be done by the server setting appropriate permissions for each client. But then the logical follow up question is, how does the server verify that the client is really who they claim to be? Authentication gives us a way to ensure that only authorized clients are able to access an API. This is typically done by the server requiring each client to provide some secret information that uniquely identifies them whenever they make a request to the API. This secret information allows the API server to validate the authenticity of this user before it authorizes any request that they make. There are several different ways of doing authentication, and here we'll cover two methods. First, basic authentication, and then API keys. Let's focus on basic authentication first. This involves each legitimate client having a username and a password for the API. An encrypted version of this username and password are combined and included within the authorization header of the HTTP request. If that header matches with the server's records, then the request gets processed, and if not, a special status code is returned to the client. This is the 401 status code. Basic authentication can be a bit dangerous because it doesn't put any restrictions on what a client can do once they're authorized. They might come in and mess with the permissions of another client, for example, which we absolutely don't want, unless that client happens to be an admin for the service, for example. These sorts of individualized restrictions can't be done using basic authentication, but they can be added by using an alternative authentication scheme known as API keys. An API key is a long random string of letters and numbers that's assigned to each authorized user. These keys are distinct from the user's password, and keys are typically issued by the service that provides the API. If you're using a key rather than basic authentication, this allows the API provider to track and limit the usage of that API. So, for example, a provider might issue a unique API to each developer or organization that wants to use its API, and the provider can then limit access to certain data. So they could limit the number of requests that each key can make in a given time period, or prevent access to certain administrative functions, like changing passwords or deleting accounts. Unlike basic auth, there's no standard way for a client to share a key with a server. Depending on the API, this might be in the authorization field of the header, or it might be in the end of the URL that's used to access the API, like we have an example of here. A third way that's slightly less common is to include the key within the body of the data somewhere. So this is good. We've learned a lot about how the internet works. And fortunately, we aren't going to have to remember this much of the time. It's mainly going to be useful information when it comes to debugging an API request that isn't quite working. In the very best case scenario, a kind developer has already written us a wrapper function for the API. These wrappers are functions in a programming language such as R that will construct the HTTP request for you. If you're particularly lucky, the API wrapper will also format the response for you and convert it from that XML or JSON format back into an R object that's ready for immediate use. One place that you might find some interesting API wrappers is R OpenSci. This is a website that has a curated list of many wrappers for accessing scientific data using R. So in this video, we'll take one API wrapper from the OpenSci website as an example. The aim here is to illustrate the important steps of getting started with a new API. The example we'll focus on is the GeoNames API, which gives some open access to a geographical database. To access this data, we'll use the wrapper functions that are provided by the GeoNames package, and much of what we'll learn will be transferable to use with other APIs. Of course, between different APIs there will be differences, and this is why it's really important that APIs, just like all of our own code, are very well documented. Before we can start using the GeoNames API, we'll have to do a little bit of setup. The first thing we have to do is install and load the wrapper package from CRAN. which can be done with these 2 lines of code. And we also need to make a user account with the API itself, which I've put a link to here. So on the right-hand side, we can see an example signup where our username is going to be example_username. Obviously, you should replace these fields with your own chosen username and email and password information. Once you've signed up, you'll get an activation link by email. And once you've followed that link, you need to enable the free web services from your GeoNames account, which you can either do directly or by following the link that I've provided here. The final step is to tell R your credentials for this API. One way we could do this is by storing it in an environment variable directly, which we could do using this code. This code would save our username as an environment variable, which is the metadata about your current R session. Environment variables control lots of things within R, like how many decimal places to print by default. Storing your API details here is a good idea because if you've got lots of API credentials, you don't want them cluttering up your working environment within an IDE. The major downside, and why you definitely shouldn't do this, is because adding these environment variables directly from your script requires you to hard code your API details into that script. If you then share the script with others, whether that's someone else in your company, with another company, or even putting your code out on the internet, you would then be sharing your API credentials with the world too. And that's definitely not a good thing to do. You want to keep them secret and you want to keep them safe. The solution to this problem then is to store your credentials as environment variables so that they don't clutter up your workspace, but to do that in a special R script that gets run each time a new R session begins. This special R script is called .rprofile, and because it has a dot on the front, it's a hidden file and won't display by default in your file explorer. The easiest way to access this type of file is to open or create it. The easiest way to access this file is to either open it or create it from scratch within an R session. You can do this using the edit R profile function from the useThis package. You can then add the previous line of code that we shouldn't put in our R script to our R profile instead. You can then save the changes to this file and restart R so that this file gets run, and your API credentials can then be accessed using the getOption function. Since your R profile file lives outside of any particular project, your credentials are then kept secret and they're kept safe. However, this also means that your work is no longer entirely self-contained and reproducible because you're relying on this R profile file that lives outside of your project. What you need to do here is make sure you give very clear instructions within your own documentation for your project on how other people should save their credentials so that they can reproduce your work. When you're doing all of this, there are 2 common gotchas, things that people do wrong. The first is that you need to make sure the R profile ends with a blank line, and you need to remember to restart R so that R profile gets run and loaded into your R session. Okay, so that's the setup done. How do we actually go about using this GeoNames wrapper package? Well, the GeoNames API has a whole host of different geodatasets that you can explore, and I've put a link here if you'd like to go and see what information is available for you. As a first example, let's try and get all of the geotagged Wikipedia articles that are within 1 kilometre of Imperial College London. So in the code here, I've started out by defining a list that gives the latitude and longitude of the South Kensington campus, and defining our search radius in case we want to expand this or contract it. We can then use the GeoNames package, and in particular the function called gn find nearby Wikipedia, to query this GeoNames API. The inputs to this function are the latitude and longitude that we care about, the search radius in kilometres, the language in which we want these articles to be, and the maximum number of results that we want to return. So let's see what this does. What this gives us back is a data frame where each row corresponds to 1 geotagged Wikipedia article. This is quite a lot of information and quite a messy format, So how about we take a look at a few of these and just do a quick check of what we're getting back. To confirm that we've got the correct location, what we can do is inspect the title of the first 5 neighbouring Wikipedia articles. There's nothing particularly surprising going on here. It's mainly departments of the college and Exhibition Road, which runs along one side of the campus. Doing these sorts of checks is really important because you can make some silly mistakes. So, for example, when I initially ran this, I forgot the minus sign in the longitude for the campus location. And I was getting results for Wikipedia articles about the East End of London rather than the West End. Fab. So we've got an example of using an API wrapper to access an API. But what about if we're trying to access an API that doesn't have a wrapper? Well, there's no need to panic here. What we can do instead is use the HTTR package to submit a GET request to the API directly. As an example here, we're going to focus on the Open Movie Database, and this is an open source version of IMDb. And what we're going to try and do is get some information about the movie Mean Girls. To do this, once again, we need to set up an API key, verify it by email, and add that API key to our R profile. So you can get an API key directly from the OMDB website, and then you'll have to click the verification link in the email that they send you. You can then add the key that you're provided with to your R profile in just the same way as we did before. And when you're doing this, remember to paste in your own API key. Don't just copy and paste this dummy string. Once we've done that, we can save the R profile with our 2 API keys saved in it now. Restart R so that these get loaded into our environment variables, and safely access our API key from within the R session. And to do this, we use get option once more, and we pass it the OMDB API key. Here we're going to store it in an object that has the same name but is all in lowercase. So now that we've done our setup, how do we actually make a request to the OMDB database? Well, looking on the OMDB website, you can see that the URL structure for any request to the API has the following form. It's going to be the URL to the OMDB API, and then following the /, we've got a sequence of characters that let us specify the query we want to make. We can specify the title we want to search for, the year, how we want the plot to be returned, and the format in which we'd like this data to be given back to us. The final part here, as we mentioned before, is going to specify our own API key to verify that we are authentic users of the API. We could type each of our queries out by hand for this, but it's much better to write our own function that can create this type of URL for any movie that we might want to look up. With a little bit of effort, we can write such a function that composes this type of URL request on our behalf. Here we're using the glue function from the glue package to neatly insert variables within a string. Okay, so let's run this example function to search for Mean Girls and store the URL that we're going to submit our request to in a value called Mean Girls request. We can take this URL that we've constructed and perform our request using the HTTR package. When we submit this GET request, the result of the function is going to be whatever OMDB's servers respond to our request. This is actually quite a complicated data object, so I'm going to store it in a variable called response, and then inspect its status code just to check that everything's gone to plan. Wonderfully, we've got a status code of 200 here, which indicates that our request was successful. And if you get a 401 error code here, if you try and replicate this yourself, check that you've clicked the activation link to your API key. This is an example of how knowing error codes can be quite helpful in debugging your API process. So as I mentioned before, the full structure of this response object is quite complicated. What we can do is easily extract the requested data about the Mean Girls film using the context function. This in itself is still quite a complicated object. It's a list with 25 elements, but you can get a vague idea of the structure of the information that we're getting back from here. We've got details about the title of the film, the year it was made, its rating, runtime, genre, director, and so on. So there we have it. Our task's complete. We've got information about the Mean Girls movie. So, wrapping up then. In this video, we've learned a bit more about how the internet works. We've also learned about the benefits of using an API to share data and how to request data from open APIs. When you're obtaining data from the internet, it's really vital that you keep your credentials safe and that you don't do more work than you absolutely have to. You should absolutely keep your API keys out of your code and store them within your R profile. And also make sure this R profile file isn't under version control as well. The last thing you want to do is put all of your secret information in a file and then put that file on the open internet. When you're obtaining information from the internet, a wrapper is always preferable to an API, which is always preferable to scraping if they have those options available to you. This buys into our whole dry framework for coding and working. We don't want to repeat work that you've already done or that others have already done. It's also important here to make sure that you're not working harder than you absolutely have to. So in our second example, we accessed an API directly, which we didn't even need to do. If we'd done a little bit of Googling, we could have seen that the OMDB API has a wrapper package, imaginatively named OMDB API, and we could have used that instead to access the API directly without having to use HTTR. So in summary, you want to make sure you're keeping your details safe and you're not doing more work than you absolutely have to. Thank you very much for your attention during this video, and I'll see you in the next one.